Шановні учасники конференції, наша конференція проходить в умовах воєнного стану через невиправдану війну, яка нав'язана нам російським агресором. Але війна об'єднала Україну, об'єднала народ з владою, об'єднала Україну з Європейським Союзом і весь світ. Україна продовжує працювати, в закладах освіти здійснюється навчальний процес. Тож від імені керівництва нашого університету, Навчально-наукового інституту телекомунікаційних систем, вітаю вас з початком роботи нашої конференції.
Dear conference participants, our conference Modern Challenge in Telecommunications is being held under martial law because of unjustified war imposed on us by Russian aggressor. The war united Ukraine, unites the people with the government, united Ukraine with the European Union and the whole world. Ukraine works in the condition of war. On behalf of the leadership of the National Technical University, Igor Sikorsky Kyiv Polytechnic Institute, and the Educational and Scientific Institute of Telecommunication Systems, I congratulate you on the start of our conference.
За своїм змістом і науково-технічною спрямованістю конференція «Перспективи телекомунікацій» відповідає сучасним вимогам до розвитку цифрової трансформації та інформатизації суспільства, інтенсивному поширенню індустрії 4.0, які є загальносвітовими трендами діяльності практично усіх розвинених країн. Базовими напрямами цих процесів є проривні інновації з розвитку технології інтернету речей та штучного інтелекту, аналізу великих даних, створення та запровадження високошвидкісних телекомунікаційних інфраструктур.
In terms of its content and scientific and technical orientation, the Modern Challenge in Telecommunication Conference meets modern requirements for the development of digital transformation and informatization of society, intensive expansion of industry 4.0, which are global trends in almost all developed countries. The basic directions of these processes are breakthrough innovations in the development of Internet of Things technologies and artificial intelligence, big data analysis, creation and implementation of high-speed telecommunications infrastructures.
Конкретними прикладами міжнародного значення цих трендів є, наприклад, виконання в нашому університеті вагомого міжнародного наукового проєкту зі створення німецько-українського центру інтелектуального з аналізу великих даних і розвитку телекомунікаційних інфраструктур. Цей проєкт виконується за кошти Міністерства освіти і науки Німеччини.
Specific examples of the international significance of these trends is the implementation of significant international project at the Igor Sikorsky Kyiv Polytechnic Institute to establish the German-Ukraine Center of Excellence for all-aided big data analysis and transport infrastructures funded by the German Ministry of Education and Sciences.
Також технічна можливість проведення нашої конференції в онлайн-форматі є хорошою ілюстрацією практичного використання сучасних інформаційно-телекомунікаційних технологій, які створені на потреби життя та стали науково-технічним базисом всеосяжної дистанційної діяльності людей планети Земля упродовж останніх 2 років за умов коронавірусних обмежень. Особливо це актуально сьогодні в Україні за умов воєнного стану.
Since the beginning of the war in Ukraine, many rich and powerful people also the technical feasibility of our conference in online format is also a good illustration of the practical application of modern information and telecommunication technologies, which are created for the life and became the scientific and technical basis of comprehensive remote activities of people on Earth over the past 2 years under condition of coronavirus restrictions and especially today in Ukraine under martial law. The following example is important here.
Тож, воєнного стану в Україні, шановні колеги, тут важливим є такий конкретний приклад. З початком війни в Україні чимало багатих та сильних людей з усього світу підключилося до допомоги нашій країні. Приєднався до Всесвітньої гуманітарної місії винахідник та найбагатший бізнесмен планети Ілон Маск. На жаль, у нього немає стільки ще космічних кораблів, щоб відправити всіх російських окупантів у космос.
Since the beginning of the war in Ukraine, many rich and powerful people from all over the world have joined in helping our country. Elon Musk, the world's richest businessman, also joined the global humanitarian mission. So far, he does not have enough spaceships to send all Russian occupiers into space.
Тож, у відповідь на прохання міністра цифрової трансформації України Михайла Федорова від 26 лютого, Ілон Маск повідомив про включення сервісу Starlink на території України і вже 28 лютого. Там було 26 лютого звернення, а 28 лютого за 2 дні перші комплекти обладнання для підключення до сервісу від компанії Ілона Маска надійшли в Україну. Упродовж наступного місяця SpaceX відправили в Україну 1000 комплектів обладнання для підключення до супутникового інтернету Starlink.
In response to a request from the Minister of Digital Transformation of Ukraine, Mikhail Fedorov, on February 26, Elon Musk announced the inclusion of the Starlink service in Ukraine. And on February 28, the first set of equipment for connection to the service from the Elon Musk's company arrived in Ukraine. Other next month, SpaceX company sent thousands sets of equipment to Ukraine to ensure connection to the Starlink satellite internet.
За словами голови Мінцифри Михайла Федорова, за останні кілька тижнів саме додаток Starlink, що забезпечує користувачам смартфонів доступ до супутникового інтернету від SpaceX, виявився найпопулярнішим в Україні. Лише один конкретний приклад цьому. Українці його завантажили вже понад 100 тисяч разів. Конкретно, один день, 13 березня, у світі було завантажень 21 тисяча разів. І найбільша кількість завантажень в цей день відноситься до України. От такі масштаби підключень нашої України до цього прогресивного Старлінку.
According to the head of the Ministry of Digital Transformation, Mikhail Fedorov, in the last few weeks, the Starlink application, which provides smartphone users with access to satellite internet from SpaceX company, has proved to be the most popular in Ukraine. Ukrainians have downloaded it more than 100,000 times. For example, the Starlink application was downloaded 21,000 times on Sunday, March 13, worldwide in both the application store and Google Play. This is the largest number of downloads in the world in one day, and most of them came from Ukraine.
Станції супутникового зв'язку Starlink вже працюють в Україні, щоб підтримати належне функціонування критичної інфраструктури та надати послуги у сфері охорони здоров'я, фінансів та енергетики.
Starlink satellite internet stations are already operating in Ukraine to support the proper functioning of critical infrastructure and services in the area of health, finance and energy.
Цікаво, що, як зазначив у своєму твіттері сам Ілон Маск, його компанія активно працює над тим, щоб адаптувати систему Starlink до нинішніх умов в Україні. Зокрема, інженери компанії працюють над тим, щоб обладнання Starlink споживало менше енергії. Крім того, увімкнули мобільний роумінг, щоб можна було підтримувати сигнал під час руху транспортного засобу.
Interestingly, as Elon Musk himself noted in his Twitter, his company SpaceX is actively working to adapt the Starlink system to the current conditions in Ukraine. In particular, the company's engineers are working to ensure that Starlink equipment consumes less energy. In addition, mobile roaming has been enabled so that the signal can be maintained while the vehicle is moving.
Останніми днями стало відомо, що Ілон Маск передав комплекти Starlink для резервування каналів зв'язку Приват-24, що дозволить за умов війни стабілізувати банківську систему України. Медичним установам та установам у сфері охорони здоров'я України передано 590 станцій супутникового інтернету Starlink. У них буде доступ до інтернету в зонах активних бойових дій, як повідомили в Міністерстві охорони здоров'я України.
In recent days, it became known that Elon Musk have transferred Starlink kits to reserve private bank communication channels that will stabilize the banking system of Ukraine during the war. 590 Starlink satellite internet stations of SpaceX company have been transferred to medical and healthcare institutions of Ukraine, and they will have access to the internet in combat zones, as the Ministry of Health of Ukraine said.
Україна щиро вдячна видатному винахіднику, бізнесмену Ілону Маску за надзвичайно велику допомогу нашій державі. Серед інших дійсно проривних на світовому рівні телекомунікацій останнього часу, окрім проєкту Starlink, ми можемо назвати сьогодні, шановні колеги, лідерські позиції Китаю щодо підключення до мереж мобільного нового покоління 5G. Так, на початку березня в Китаї налічувалось близько 1,4 мільйони базових станцій 5G та понад 500 мільйонів 5G-користувачів. Згідно з офіційними прогнозами, країна планує збільшити кількість базових станцій 5G цього року до 2 мільйонів користувачів. Очікується кількість мереж до 2023 року ще до 560 мільйонів. В результаті охоплення користувачів мобільних телефонів мережами нового покоління перевищить 40%. Це дійсно унікальні масштаби застосування технології 5G, от на прикладі цієї великої країни.
Among other the truly breakthrough telecommunications technologies of recent times, apart from the Starlink project, are China's leadership in connecting a new generation of 5G devices to mobile networks. By early March, there were about 1,043,000,000 5G base stations and more than 500 million 5G users in China. According to official forecasts, the country plans to increase the number of 5G base stations to 2 million this year. It's expected that the number of 5G subscribers will reach 560 million by 2023, resulting in coverage of mobile phone users with new generation networks will exceed 40%.
Південна Корея також досягла швидкого прогресу в швидкості та покритті мережі 5G, оскільки була першою країною, яка комерціалізувала послуги 5G у квітні 2019 року. Сьогодні Південна Корея продовжує підготовку до запровадження ери 6G з метою комерціалізації цієї технології в 28-30 роках, плануючи запустити комерційну мережу 6G, яка буде в 50 разів швидше, ніж поточний сервіс, і розширить покриття до 10 кілометрів над землею. Дослідження зі створення засобів 6G технологій вже охоплюють сьогодні терагерцовий діапазон частот, про що ми сьогодні почуємо, шановні колеги, у цікавому виступі професора Оберхаммера.
South Korea has also made rapid progress in speed and 5G coverage, as it was the first country to commercialize 5G services in April 2019. Nowadays, South Korea continues to prepare for the 6G era to commercialize the technology from 2028 to 2030, planning to launch a commercial 6G network that will be 50 times faster than the current services and expand coverage to 10 kilometers above the ground. Research on the creation of 6G technologies already covers the terahertz frequency range, which will be here today in an interesting speech by Professor Oberhammer.
Новації в сфері ІКТ впроваджуються і в нашій країні. Так, наприклад, продовжуючи залучати інвестиції в автономний 5G, Vodafone сьогодні оголосив про успішне лабораторне випробування, проведене разом з Ericsson, автоматизованого створення мережевого фрагмента, налаштованого для підтримки віртуальної реальності у роздрібному середовищі. За даними Vodafone, від моменту розміщення замовлення до створення мережевого фрагмента для передачі реального мережевого трафіку знадобилося 30 хвилин. Оператор повідомив, що фрагмент гарантовано має швидкість завантаження 260 Мбіт в секунду, швидкість завантаження 16,5 Мбіт в секунду і затримку 12,4 мілісекунди.
Innovation in the field of information and communication technologies are being implemented in our country. For example, while continuing to attract investment in autonomous 5G, Vodafone company today announced a successful laboratory test conducted with Ericsson for automated creation of network fragment configured to support virtual reality in retail environment. According to Vodafone, it took 30 minutes from the moment the order was placed to the creation of the network fragment to transmit real network traffic. The operator said that the fragment guaranteed has a download speed of 260 megabit per second, upload speed of 16.5 megabit per second, and delay of 12 milliseconds.
Розширенню застосувань ІКТ в Україні безумовно сприятиме те, що місяць тому президент України підписав закон про хмарні послуги. Тепер державні органи зможуть зберігати дані у хмарних сервісах.
The fact that the president of Ukraine signed a law on cloud services a month ago will contribute to the expansion of ICT applications in Ukraine. Now, government agencies will be able to store data in cloud services. In order to process more and more information, authorities and local governments need to be periodically increase the amount of computing and human resources.
Також важливим є те, що міністр цифрової трансформації Михайло Федоров підписав лист, у якому закликав не мобілізувати IT-фахівців. Він вважає, що айтівцям варто зосередитися на кібервійні, а також продовжувати працювати та платити податки.
It's also important that the Minister of Digital Transformation, Mikhail Fedorov, signed a letter urging not to mobilize IT specialists. He believes that IT people should focus on cyber warfare as well as continue to work and pay taxes.
Для покращення якості підготовки фахівців у сфері ІКТ нашим Інститутом телекомунікаційних систем запроваджено проєкт, в рамках якого наші студенти та викладачі в телеграм-каналі Деканат ІТС майже щодня отримують інформацію про новини в сфері ІКТ. За останній рік нам вдалося повідомити про 500 плюс новин. Про цей проєкт та його результати буде йти мова на нашій конференції у виступі доцента Ірини Кононової.
To improve the quality of training of ICT specialists, our Institute of Telecommunication Systems has implemented a project in which students and teachers in the Telegram channel of Dean of ITS receive almost daily information about news in the field of ICT. We have reposted more than 500 news stories in the last year. This project and its results will be discussed at our conference in the speech of Associate Professor Irina Kononova.
Шановні колеги, наша конференція має на меті інформувати вчених і суспільства про новітні результати останніх наукових досліджень в сфері інформаційно-телекомунікаційних технологій. В нинішніх умовах в Україні серед заявлених близько 100 потенційних учасників є представники з 8 країн, зокрема Китаю, Німеччини, Швеції. Вчені України представляють сферу науки в 17 провідних наукових установах і університетах з міст Києва, Харкова, Житомира, Львова. Тези доповідей, які включені до програми конференції, будуть представлені як в електронному вигляді, і їх вже отримали учасники, а також буде опубліковано повний текст в паперовому варіанті, а найбільш вагомі доповіді будуть рекомендовані для публікації в міжнародному журналі наукових досліджень Information and Telecommunication Sciences.
Dear colleagues, our 16th Annual International Scientific and Technical Conference, Modern Challenge in Telecommunications, aims to inform scientists and societies about the results of the latest research in the field of information and telecommunication technologies and radio electronics. In the current difficult conditions of martial law in Ukraine, among the declared of about 100 potential participants are scientists from 8 countries, including China, Germany, Sweden. Ukrainian scientists represent science in 17 leading research institutions and universities in Kyiv, Kharkiv, Zhytomyr, Lviv.
Шановні учасники конференції, маю можливість щиро подякувати всім особам, завдяки діяльності яких стало проведення нашої 16-ї щорічної конференції. Я дякую усім авторам доповідей, які знайшли можливість розповісти про свої наукові здобутки у форматі нашої конференції. Наша повага членам організаційного комітету, рецензентам, які провели об'єктивний розгляд наданих доповідей. Щорічна конференція поєднує науково-практичні інтереси партнерів і постійних учасників, що представляють нашу сферу IT плюс телекомунікації, і це є повсякденною діяльністю наших фахівців, які успішно працюють в Україні за цим напрямком.
Dear conference participants, I have the pleasant opportunity to sincerely thank all the people who made it possible to hold our 16th annual conference. Conference Modern Challenge in Telecommunications occupies a leading position in the ranking of all other 70 scientific conferences which hold in Igor Sikorsky Kyiv Polytechnic Institute. I thank all the authors of the reports who found the opportunity to talk about their new scientific achievements in the format of our conference at this difficult time for Ukraine. Our respect to the members of the organizing committee and reviewers who conducted an objective review of the submitted reports. Our annual conference combines the scientific and practical interests of partners and regular participants representing 17 leading universities and research institutions which are associated with the daily activities of scientists who successfully work in the field of information technology and telecommunications in Ukraine.
Моя персональна особлива вдячність за участь в нашій конференції відомому в світі вченому і активному організатору багатьох IEEE конференцій, науковому координатору проєктів з терагерцевих технологій, редактору журналу IEEE Transaction and Terahertz and Technology, доктору філософії, професору Королівського технологічного інституту в Стокгольмі, Швеція, Йоахіму Оберхаммеру. Змістовний виступ професора Оберхаммера ми сьогодні послухаємо на нашій конференції. Я щиро вдячний професору Оберхаммеру за те, що місяць тому він особисто підтримав пропозицію нашого інституту щодо участі в конкурсі рамочних грантів дослідницької програми Швеції «Обчислювальні та апаратні засоби для інфраструктур ІКТ». Ця програма спрямована на забезпечення наступного покоління бездротових комунікацій 6G, підсилення обчислювальної потужності та енергоефективності інформаційно-комунікаційних технологій. У рамках цієї програми професор Оберхаммер є керівником проєкту з нових терагерцевих технологій бездротової передачі даних. До складу виконавців цього проєкту долучено вчених нашого Інституту телекомунікаційних систем КПІ імені Ігоря Сікорського.
My personal gratitude for participating in our conference to Joachim Oberhammer, who is the world-famous scientist and active organizer of many IEEE conferences, scientific coordinator of projects on terahertz technologies, the editor of the IEEE Transactions on Terahertz Science and Technology magazine, and also Doctor of Philosophy, professor at the KTH Royal Institute of Technology in Stockholm, Sweden. We will hear a meaningful speech by Professor Oberhammer at our conference today. I am sincerely grateful to Professor Oberhammer for personally supporting our institute's proposals a month ago to participate in the competitive grant competition of the Swedish research program Computing and Hardware for ICT Infrastructures. This program aims to provide the next generation of wireless communications, 6G, enhance computing power and energy efficiency of information and communication technologies. As part of this program, Professor Oberhammer is the leader in new terahertz wireless technologies projects. Scientists of our Institutes of Telecommunication Systems also include as participants of this project.
Тож, шановні колеги, учасники конференції, бажаю всім нам успішного проведення конференції. Дякую за увагу. Усім вам добра. Разом до перемоги.
So, dear colleagues, I wish you a successful conference. Thank you. Good luck to all of you and together to victory.
Шановні колеги, я хочу запросити до подальшого англомовного ведення як співкоординатора пленарного засідання нашої конференції, першого заступника директора ІТС, кандидата технічних наук, доцента Авдієнка Гліба Леонідовича, який якісно супроводжував мій виступ на даній конференції. Прошу, Глібе.
Dear colleagues, I invite Avdiyenko Gleb, the first Deputy Director of ITS, Doctor of Philosophy, Associate Professor of Department of Telecommunications for further English language supporting, as the co-moderator of the plenary session of our conference. So it's me. So dear colleagues, we'll continue our greeting speech, and now we're pleased to welcome at our conference head of the Scientific Research Center for Digital Transformation and Law of the Scientific Research Institute of Informatics and Law at the National Academy of Legal Sciences of Ukraine, Doctor of Law, Professor Alexander Baranov. Professor Baranov, please begin your speech.
Дякую за надане слово. Шановний пане співголова, шановні учасники, щиро вітаю вас з відкриттям та початком нашої сьогоднішньої конференції. Я ще раз декілька слів скажу щодо того, що конференція готувалась та почала свою роботу в надто важкі часи для нашої країни. В часи здійснення безпідставної військової агресії зі сторони безпринципного та безжалісного ворога Російської Федерації, який на сьогодні підступно та злочинно атакує всіма можливими засобами цивільне населення і цивільну інфраструктуру.
Dear co-chair, dear participants, I sincerely congratulate you on the opening and starting of the conference. The conference was being prepared and started. It works in very difficult times for our country. At a time of unjustified military aggression by an unprincipled and ruthless enemy of the Russian Federation who insidiously and criminally attacks the civilian population and civilian infrastructure by all possible means.
Але сам факт проведення конференції і наша з вами участь в ній – це є свідченням нашої віри в перемогу та подальше відновлення нашої батьківщини. Саме така віра є рушійною силою супротиву Збройних сил України, всього нашого народу і всієї телекомунікаційної спільноти.
But the fact of holding the conference and your participation in it is a testimony of our faith in the victory and further restoration of our motherland. Such the faith is a driving force for the armed forces of Ukraine, all the people and the telecommunication community to fight the aggressor.
Трохи слів про обстановку і телекомунікаційній спільноті. Я є учасником різноманітних пабліків в соціальних мережах. Це і оператори телекомунікацій, і айтішники, і IT-юристи, і юристи інших напрямів діяльності. Наприклад, найбільша телекомунікаційна спільнота в пабліки об'єднує понад 1500 керівників і фахівців, а за добу в неї відбувається десь біля понад 1000 повідомлень.
I am a member of various publics on social networks, telecommunication operators and providers, IT technicians, IT lawyers, other communities of lawyers of various profiles. For example, the largest telecommunications community unites more than 1,500 managers and professionals. They are up to 1,000 messages per day in it.
Наприклад, серед таких повідомлень десь тижня 3 тому було таке повідомлено від одного з провайдерів. Необхідно відновити зв'язок між точкою А та точкою Б, це десь в районі Харкова відбувалося. Прошу тих, хто може допомогти це зробити за рахунок своїх мереж, надати умови для домовленостей щодо проведення робіт. І вже через 4 хвилини відповідь повідомлення іншого провайдера. Взяв до роботи, технічні підробиці надіслав у приват.
Among such messages about 3 weeks ago was a message from one of the providers. It's necessary to restore the connection between point A and point B. I ask those who can help to do this through their networks to provide conditions for arrangement for work. In 4 minutes, response message from another provider. Took to work, send technical details to private message.
І я скажу, що саме так сьогодні працюють українські і телекомунікації. Працюють без економічної конкуренції, але з конкуренцією допомоги кожен кожному. Така ситуація є типовою, і це є предметом гордості за нашу галузь.
This is how Ukrainian telecommunications works today. They work without economic competition, but with competition to help everyone. This situation is typical and it's a matter of pride for our industry.
Але ж ми з вами на конференції, і мені треба щось сказати про наукові дослідження. Тематика наукових досліджень, результати яких запропоновано до розгляду на конференції, є актуальною та корисною для галузі, але вже настав час поміркувати про додаткові теми, які нам диктує сьогодення.
But we are with you at the conference, and I need to say something about research. The topics of scientific research, the results of which were proposed for consideration at the conference, are relevant and useful for the telecom industry. But it is time to think about additional topics that are dictated to us today.
Ми маємо розуміти, що за останні майже 2 місяці нашого життя ми вже отримали справжню скарбницю інформації щодо практичного досвіду на швидкоруч вирішених та ще більше невирішених проблем, помилок та винаходів щодо організації зв'язку, експлуатації мереж і телекомунікацій та надання послуг населенню нашої країни, військовим, державі в надскладних умовах.
We have to understand that in the last almost 2 months, we have already received a real treasure trove of information about practical experience, hastily resolved and even more unresolved problems, errors and inventions regarding the organization of communications, operation of telecommunication networks, and the provision of services in extremely difficult conditions.
Україна вже отримала великий масив інформації, і він є в різних пабліках, в різному досвіді, надто корисний для наукових досліджень та узагальнень.
Ми робили, нам сказали спочатку, що ми правильно підпишуть успоки, а тоді сказали, що вибачте, будь ласка,
Для наукових досліджень та узагальнень. Виявлено цікавих перспективних тем для наукового пошуку. Але цей масив начебто є, але його поки що нема. Тому що поки вчені не зроблять те, що належно їм робити, він не буде доступний до широкого загалу.
Ukraine already have this large data array that is very useful for research and generalizations, identifying interesting, promising topics for research. But this array seems to exist, but it does not exist until scientists do what they supposed to do.
Які ж завдання в додаток до тієї актуальної тематики, що сьогодні розглядається, можна було б сформулювати на майбутнє? Ну, наприклад, це збір і узагальнення системних проблем, з якими стикнулися оператори та провайдери. Що може бути? Так, на скору руку скажу, що це може бути збір та узагальнення практичного досвіду побудови гібридних мереж телекомунікацій на основі використання супутникових технологій, наприклад, Starlink, Ілона Маска, про які так сьогодні чудово доповідав Михайло Єфимович.
What task in addition to the current scientific topics could be formulated for the future? Firstly, collection and generalization of system problems faced by operators and providers. Secondly, collection and generalization of practical experience in building hybrid telecommunication networks based on the use of Starlink satellite technologies of Elon Musk.
Далі така група тем, як оновлення теоретико-методологічних засад проєктування та оперативної побудови гібридних мереж телекомунікацій в умовах надзвичайного та воєнного стану, в умовах ведення воєнних дій. Розроблення сучасних і теоретико-методологічних засад та практичних рекомендацій щодо проєктування та побудови електронно-комунікаційних мереж інтернет із забезпеченням безпеки та сталості, що ми практично втратили за останні декілька років. Прошу.
Update of theoretical and methodological base of designing and operating construction of hybrid telecommunication networks in the conditions of state of emergency and martial law conducting military actions. Also, development of modern theoretical and methodological principles and practical recommendations for the design and construction of electronic communication networks internet with security and sustainability.
Кардинальне перероблення і вдосконалення правових, організаційних, технологічних та технічних засад функціонування національної системи оперативно-технічного управління телекомунікаційними мережами в умовах надзвичайних ситуацій, надзвичайного та воєнного стану. До речі, скажу, що документ був в свій час прийнятий в 2004 році і з того часу майже не коригувався. Далі розроблення практичних рекомендацій та проєктування і побудови з забезпеченням сталого функціонування електронно-комунікаційних мереж з врахуванням можливості сьогодні операторів взаємного використання своїх інфраструктур і ресурсів мереж відповідно до нового закону про електронні комунікації.
So, radial revision of legal, organizational, technological, and technical basis of functioning of the national system of operational and technical management of telecommunication networks in the conditions of emergency situations, state of emergency, and martial law. Development of practical recommendations for the design and construction with ensuring the sustainable operation of electronic communication networks, taking into account the possibility of access to electronic communication networks and their infrastructure.
І на останнє це розроблення технічних рекомендацій щодо побудови тактичних систем радіозв'язку поля бою, розроблення пропозицій щодо можливої організації національного виробництва таких систем у кооперації з іноземними виробниками.
Finally, development of technical recommendations for seamless interconnection of electronic communication networks with different data transmission technologies. Development of technical recommendation for the construction of tactical radio communication systems on the battlefield. Development of the proposals for organization of national production of such system in cooperation with foreign manufacturers.
Звичайно, це теми, які є орієнтовними хоча б для того, щоб розхитати нашу творчу фантазію. І закінчуючи своє привітання, скажу, що бажаю всім нам успіху в проведенні конференції, взаємного збагачення ідеями і досвідом. А також бажаю вам і собі теж міцної віри в перемогу та мирне майбутнє. Дякую за увагу.
So, with a purely indicative direction in order to shake our creative imagination, I wish all of us success in holding the conference, mutual enrichment of ideas and experience. I wish you strong faith in victory and a peaceful future. So, thank you, Alexander Andreevich, for your speech. And now, according to our conference timeline, we're moving forward. And now our first plenary session speaker is Professor Joachim Oberheimer from KTH Royal Institute of Technology in Stockholm, Sweden. Dear Professor Oberheimer, your speech, please.
Thank you very much, Gleb, for the introduction, and thank you very much for the invitation to Professor Mikhailo Ilchenko and to Professor Alex Tsikov for inviting me to this conference. I think your country is going through very difficult times at the moment, but it is very important to keep the scientific spirit up and to continue and to start new collaborations, international collaborations. And this happened now recently very successful with Professor Tsikov and us at KTH. And I'm very glad to be able to support you by giving a short presentation at this conference. So the topic of the conference is challenges, modern challenges in telecommunication. And one challenge is new frequencies. New telecommunication standards and the increasing data rates need to go to higher frequencies and to access new frequency spectrum. And for that reason, it is important to access the terahertz frequency spectrum. And there are many technical challenges in terahertz frequencies. And we are trying to address this in my research group by developing terahertz microsystems with the idea that this kind of new technology could enable the large-scale exploitation of these new frequency bands at terahertz frequencies. So if you look at what are terahertz frequencies, there is an important frequency gap between the domain of electronics or microwaves and the domain of photonics. And that is the so-called terahertz gap, which is between 100 gigahertz and 10 terahertz. And they are very large unused frequency bands for sensing, telecommunication, and joint communication and sensing, or called JCAS. And within the 6G standard, which was already mentioned in the beginning, there is actually terahertz bands are mentioned. So when we evolve towards sixth generation of telecommunication, the terahertz bands will play an important role because they enable us to go to terabit per second. Furthermore, at these higher frequencies, you can get very small high gain antennas. So everything is very small because of the smaller wavelengths. So you can have large scale antenna arrays, which are very, very small, and thus easy to integrate in buildings, for instance, or also on smaller devices. There are, however, a lot of challenges at terahertz frequencies, and that's new technology and new system solutions are needed. And also telecommunication has to fight with limitations to short distances or short ranges, because it's very difficult to get high power to have long distance telecommunication at these terahertz frequencies. So there is already a variety of terahertz applications beside telecommunication, and the three main application groups in terahertz frequencies are imaging, spectroscopy, and then communication. Radio astronomy has been very early in exploiting terahertz frequencies, like in radiometer applications. And also security applications have very early started to exploit terahertz frequencies, like for detection of concealed weapons, for instance. Terahertz frequencies are very important for high resolution radar, and that can be defense applications, but also civil applications. And we see currently that car radar, so automotive radar, is very heavily pushing towards terahertz frequencies because they need higher resolution in the context, for instance, of autonomous driving. Other applications are for medical diagnosis, because terahertz frequencies have specific properties in characterizing materials. It can be used for spectroscopy, like for detecting explosives, detecting certain chemical substances. Terahertz frequencies play an important role in Earth observation. So this is satellite-based radiometers, for instance, for weather satellite, weather monitoring, but also monitoring atmospheric pressures, atmospheric parameters, and environmental changes in the world. So for this purpose, terahertz frequencies are already exploited as well. Terahertz plays also an important role in material inspection because of the high resolution. You can get the high resolution images, which you might not get with other means. And it's a non-ionization radiation as compared to X-ray, for instance. And terahertz can also be used for bioimaging. And finally, terahertz frequencies are getting more and more interesting for telecommunication. And in the way towards 6G and to very high bit rates, we will need to exploit terahertz frequencies. I would like to say a few words about my research group at KTH. So we are 16 people now, and I have 4 senior researchers And one of them, Dr. Alexander Glubakov, he actually is from your university. So he did his master degree in Kiev at your university. And he's one of the most important members in my group. And he has excellent knowledge and background in microwave engineering. So I'm very strongly convinced that your university has an excellent education. And I'm very glad that he's a member in my research group. I also would like to say that I have two members from Russia, so Dr. Dmitry Lubchenko and Dr. Sergei Smirnov. And this is an example that scientists, we have to work together internationally, and we can be good friends despite very bad political leaderships in certain countries. But scientists should always try to keep working together. We have a terahertz measurement laboratory. So we can measure up to 750 gigahertz at KTH. And we have several custom-made measurement setups, like this terahertz probe station. And we have also a terahertz antenna measurement chamber, which is custom designed because this kind of equipment is not possible to purchase because it's at the frontier of science. So we had to design both this probe station and this antenna measurement chamber since it's not commercially available. Yeah, I would like to say something about our background. The technology which we are using comes from semiconductor manufacturing. So the same fabrication processes which are used to manufacture microelectronics or microprocessors, which clearly have revolutionized the information age. The same fabrication processes can be used to do miniaturized mechanical systems, which is called microelectromechanical systems, or silicon micromachining, or MEMS. And this kind of technology has revolutionized many sensors. And our mobile phones nowadays contain many of these micro-machined sensors, like accelerometers, gyroscopes, inertial sensors, microphones. They are all fabricated by this enabling technology. And they clearly have revolutionized sensors and user interfaces in the modern world. The same technique, the same technology has been used also in the radio frequency world. So 20 years ago, people started using this technology for making radio frequency devices, which was called RF MEMS, like miniaturized switches and tuning circuits for mobile phone antenna tuners. And what we are doing now, we are going the next step. Next step is using this kind of technology for solving technical problems in this terahertz gap. And the vision of our research work is that this kind of silicon micromachining technology could enable or revolutionize the exploitation of the terahertz spectrum. And I will show you soon in which way we are thinking. So first of all, in this frequency range, we work with rectangular waveguide technology. So we don't have transmission lines, but everything is based on rectangular waveguides because of the low losses. And this here is a conventional terahertz system. It's by a company in Germany. So these are receivers like at 660 gigahertz or 448 gigahertz. And this is a very high performance technology. But from a manufacturing point of view, I would call it's still in the Stone Age. It's very underdeveloped. And that's because this is based on CNC milled metal blocks. They are very bulky, very heavy. They need manually to be assembled. They're very expensive. And they can only be used for very expensive or scientific instruments. And this is not volume manufacturable. So current terahertz technology cannot be manufactured in larger quantities, even if there would be upcoming terahertz applications. This technology is not scalable to larger frequencies. So the vision of us and also other research groups in the world is to use this silicon micromachining. So the same fabrication technologies, which is used for microelectronics, and to use this technology and put this on a single chip, on a single microchip, where you have the waveguides, you have integrated waveguides here, you have antenna interfaces, you can have filters, you can have phase shifters, you can have power combiners, sensor interfaces. So any kind of electromagnetic components which you need for a complete system, you can integrate on a single small chip. And this is much, much smaller, lighter, much lower cost, significantly less power consumption. And the key thing is this is volume manufacturable, because this can utilize microelectronics manufacturing facilities. So this technology platform will be an enabling factor in exploiting the terahertz frequency spectrum on a large scale, because this kind of technology can only be used for scientific instruments and not for larger applications. So on this way, we have been working on many devices at KTH, and I will show you a few examples soon about that. So if you would like to make this complete system, you need a large toolbox of different electrical components. Like the first thing is you need waveguides, and we have currently the world record in the world's lowest loss waveguides, and that's enabled by this micromachining. So we have very low losses in different frequency bands. We are using this technology for making filters, and also on filters, and that's where my colleague Alexander Glubokov is working on. So filters is his specialty. So we have shown extremely high Q factors, like Q factors of close to 1000 at 700 gigahertz, and Q factors beyond 1000 at lower frequencies in the D band. And this kind of performance is totally impossible with any other technology. So you need this silicon micromachining for achieving this performance. We have been working on phase shifters. Phase shifters are very important components in reconfigurable systems, in particular when it comes to antennas and beam steering. And we have shown these phase shifters up to 750 gigahertz. We also worked on waveguide switches for reconfigurable circuits, so electromechanical waveguide switches. We did work on antenna arrays. I will show you some examples of that. And antennas, of course, are essential to telecommunication links. We also did some work on medical sensor interfaces. And of course, there's a number of other components which you need in a complete microwave system, like integrated absorbers. You need power dividers or power combiners. You need couplers and many other components. And of course, we can also integrate active circuits. So MMICs, and we have been working on integration of MMICs both on silicon germanium and indium phosphide and gallium arsenide technology into our waveguide platform. So this is the basic activities in my research group. We are trying to miniaturize and to integrate all the necessary circuit functions which you need for a complete microwave system onto a single chip, and this will enable the large-scale utilization of terahertz frequencies for many applications. So now I show you a few selected device and project examples of what we have been doing at KTH. I started the filters. So this is the work of Dr. Alexander Glubokov. And we have been the first ones showing very, very high Q factors at the sub-terahertz frequencies. This year was our very first filter demonstrator at 270 gigahertz. It's kind of quite a narrow band device, and we had unloaded Q factor of 800 of this 4-pole and 2 transmission stereo filter. And this was a world record by the time. And here is his latest development, and that's now at 700 gigahertz. Also here, very narrow band and very high Q factors. So we have even higher Q factors here. And this is also world record. And this device actually broke several world records. These devices are also the first sub-millimeter wave 1% fractional bandwidth filters. We are utilizing this technology also for lower frequencies. So now we talk about the D-band. D-band communication links. These are very important for telecommunication companies like Ericsson, Huawei, and Nokia. They are spending right now very big effort into developing point-to-point communication links at these frequencies. So we have done a Diplexer filter, where you have one RX receiver and a TX transmitter and a common antenna port, and you have a filter structure in between. And here you see the performance of this D-band diplexer, where it's important to have a low insertion loss, very low insertion loss, even lower here for a single filter, and very high adjacent channel isolation. So the isolation between two adjacent channels must be in the order of 60 decibel. We have also been using this on a system level. So this is actually our very first system demonstrator. This is now a complete front end, the complete front end functionality of a D-band telecommunication link on a single chip. It's 2 centimeters times 1.5 centimeters. You see here this diplexer filter. So this is the diplexer filter here. And you see the silicon germanium MMICs for the TX, for the transmit, and for the receiver. You see the chip here is inserted into this platform, and the platform contains all type of auxiliary components like bypass capacitors, the routing lines, the wire bonding, and so on. And this was a collaboration with Ericsson in Sweden and Infineon doing the silicon germanium circuit. So these were the main players in this project, among other players like Chalmers University in Sweden and other companies were also involved in this project. I show you something more about antennas, because antennas are very important in telecommunication. These are two antennas at quite high frequencies, so 320 to 400 gigahertz. You can achieve very large bandwidths. So here we have a 80 gigahertz analog bandwidth, and this is an array which contains 16 times 16 antenna elements. So we have in total 256 antennas, and it's very small. So you see, this is the size of a thumbnail, 12 millimeter, very, very small for more than 200 antenna elements. We have a high directivity, 33 dBi, and also very high gain. So the loss, the total loss of this array, including the power distribution network, is less than 0.8 dB. And this is because of our very low loss technology. So we have a very high radiation efficiency, despite these very, very advanced frequencies. Here is an even bigger array. This is much larger. This is now 32 times 32 antenna elements. So 1024 antenna elements. It's still quite small. So it's about 24 millimeters. The chip is still very small. And we have now even higher directivity, of course, 6 dB higher directivity, and also very high gain, a bit higher losses, but it's a very, very high gain antenna array. And you can have a half power beam width. So this is the measured beam width, half power beam width of 1.7 degree. It's a very, very high directive, very narrow beam, and very, very small. So this shows really also the potential of miniaturizing antennas at these very advanced frequencies. Here's another example of a frequency steerable high gain antenna. I'm not going to explain how this works because it's a very complex microwave system. But essentially, we are using waveguides, parallel plate waveguides on different layers. We have coupling in between. We have integrated reflector. We have leaky wave antenna array. And in the end, you get this pencil-shaped beam, this radiation beam, and it can be moved or steered by the carrier frequency. So for different frequencies, and this is now for 240 to 290 gigahertz, we can steer the beam within a 55-degree field of view. And we have also shown a very basic radar demonstrator for this. And it's also very small. This is 24 millimeter long and about 1 millimeter thick. So it's a very compact device. I want to show another example, which shows a very complex geometry. So this is a OMT, auto mode transducer. And this is a nice example that we can do very, very complex geometries by this silicon micromachining. So this is the basic device. So basically you have one rectangular waveguide port, which is for one polarization, and another rectangular waveguide port for the other polarization. And you're combining both signals in this common square shaped port here. And this device is very complex. You see, it has many small features, many small elements here. We have power splitters, we have different routing, and we have a four-way power combiner here in the center. So this is done by 3 chips, which contain multiple layers each. And it's also very small. It's only 1 centimeter large. The most important performance parameters here are the insertion loss. You want to have low insertion loss. Insertion loss here for both channels is better than 0.6 dB for the whole waveguide band. So this is very broad band. So we have 110 gigahertz bandwidth, very large bandwidth. And also you want to have a low leakage between the horizontal and the vertical polarization. So you want to have very high cross polarization isolation. And we have that of this device in the order of between 70 and 50 dB isolation. So 70 to 50 dB is the floor, and there's just a few spikes which go up to 35 dB. So you can achieve very, very high performance polarization combiners with this kind of technology. This is another example. It's a phase shifter. Phase shifters are very important for beam steering applications like phased arrays. And these are 220 to 330 gigahertz. I'm not going into details how this is working, but essentially we have dielectric bodies, dielectric objects inside a waveguide. This is a rectangular waveguide. And we can move them around by having micro actuators. And when we move around this geometry in the waveguide, we get a different phase shift. So we have shown here in the middle of the band, we can have 440-degree phase shift. And it's a very linear phase shift. So we also have a full band device here. So it's extremely broadband, 110 gigahertz bandwidth we can achieve here. And the total phase error, and this includes the whole frequency spectrum and any phase state and the whole frequency spectrum, is actually the worst case phase error is better than 4 degrees. And the insertion loss is in the order of better than 2.5 decibel. And this kind of device is also impossible to do with this performance in any other technology. Yeah, I would like to show you some projects and how we are using this. One important application field is the car radar. So we are using terahertz frequencies for car radar. We have a European project. So European collaboration, and here we actually are putting a complete car radar front end at 240 gigahertz on a small microchip. And this is currently in fabrication here at KTH. And during autumn, we are going to do the first tests. So this microchip contains a 2x8 antenna array. It's reconfigurable antenna array. We have amplitude tapering. We can do 2-dimensional beam steering. We can do beam shape switching. So we have integrated reconfigurable structures that we can actually switch between different beam shapes. So it's not only beam steering, but also beam shape switching. And we are using artificial intelligence and computational imaging algorithms for the data and the signal processing. Another example I want to show you is for Earth observation. So this is for satellite-based environmental sensing. And this is a collaboration project with ESA, the European Space Agency, and the German company RPG. So this is a new generation of radiometer, which is miniaturized by this micro machining technology, which we have at KTH. And the idea is that in the future, you will not have one single, or currently there are 3 weather satellites above Europe, but in the future, you will have a network of hundreds of weather satellites, and they will monitor, they will observe the weather all over Europe. And these satellites will be very small in these satellite networks. And for that, you need to miniaturize your scientific instruments. So this will be used for a radiometer calibration platform for spaceborne environmental sensing satellite networks. We also have a new project on Terahertz Communication, and this was mentioned in the very beginning already. So here we want to do something very advanced. We want to go to 800 gigahertz. So we are working on completely new architectures which enable telecommunication at 800 gigahertz. And telecommunication is very important in Sweden because of companies like Ericsson, for instance. And therefore, we are really kind of building the fundamentals for Terahertz communication at these very, very advanced frequencies. So we are targeting here 800 gigahertz and 150 gigahertz analog bandwidth at this kind of frequency. And you can actually do with this even beyond 10 terabit per second. I also have a European project where we do a large-scale integrated array. And this is a massive MIMO. Massive MIMO system at terahertz frequencies. This is an array with 1024 antennas. It has different subarrays, and the subarrays can steer the beams in different directions. So this is a true reconfigurable MIMO system, multi-input, multi-output system on a massive scale. And this will be done at 400 gigahertz. And something like that has never been done before. Yeah, let's come to some conclusions to keep the time. So sub-terahertz frequencies, we are talking here about 100 gigahertz to 1 terahertz. They are already now exploited. So there are many applications already now. I think telecommunication will benefit from this ongoing technology development. So other applications like car radar have been much faster in going into these higher frequencies. And I believe telecommunication and 6G will benefit from terahertz technology development. New technology and new system integration solutions are needed for terahertz frequencies. So we have to solve many technology problems, and we need new system integration solutions, in particular for large-scale exploitation of these frequencies. And telecommunication at some stage will always go over to large-scale exploitation and not only to single high-end communication links. So we are pretty convinced that this silicon micromachining, so silicon micromachining is the technology which I was showing you today, which basically means that you put a whole terahertz system on a single silicon micromachine chip. So this silicon micromachining is a very promising technology for giving very high performance, highly integrated, and volume manufacturable sub-terahertz devices and systems. Yeah, I think at KTH we are combining competence in, we can do very complex microwave system design, and we have a competence in this microfabrication. And yeah, we have the measurement facilities to 750 gigahertz. So from that point of view, we are, I think, a good player in this kind of new technology. So with this, I would like to finish my talk, and I hope it was interesting for you, and to show you a new technology, which for sure will play a key role in exploiting terahertz frequencies. And if you have any questions, I would be glad to take these questions now. And thank you again for inviting me to your conference.
So, dear colleagues, do you have any question to Professor Aberhan?
Yes, I have one question. Very simple. What kind of resonators are you using in the filters?
Yes, we are doing filters with different types of resonators. So this filter and this one here, so these are of course all cavity resonators, and these are dual mode cavity resonators. So here we have 4 poles and 2 transmission zeros. So we have here the 4 poles and the 2 transmission zeros, and the 4 poles are created by having 2 coupled dual mode cavity filters. And the same is also done here. So here we have a similar configuration, also with 4 poles by 2 coupled cavity resonators. We don't have the transmission zeros here, so we don't have this additional coupling which we have here. And what we are doing here, you might wonder why do we have higher Q factor at higher frequencies? Because usually the Q factor should go down with frequency. So here at lower frequencies, we have this Q factor of 800, and at roughly 3 times higher frequencies, we have an even higher Q factor. The reason for that is that we are overmoding these resonators. So in this example, we use the fundamental mode of the resonators, but in this example here, we are overmoding the filters, and then you have a lower influence of the losses from the metal, which is confining the cavity around the filters. So that's the reason why we get higher performance here at higher frequencies. Does it answer your question?
Thank you very much. But you have very high very high Q factor of the resonators.
Yes.
What metal you are using for them?
We are using gold. This is gold. The main reason for the high Q factor at these frequencies, the most important factor is the surface roughness. So the silicon micromachining can give you a surface roughness of 2 nanometer. And with 2 nanometer, and then you don't need much gold. So we typically put on half a micrometer of gold, like 500 nanometer gold. And then you can achieve these very high Q factors. But the single most important factor is the surface roughness. So this technology gives a surface roughness of in the order of 2 nanometers, depending on the walls. Some walls have 10 or 50 nanometers, but the majority of the walls can have a very, very low surface roughness. And this is the reason why we have the best performance of any filters in this frequency range of any other technology, because no other technology is able to create this low surface roughness.
Do you think about dielectrics using for the filters?
Yes, actually, we are working also on that. We are working on dielectric resonators. And the main reason why we do that is because then we can go to much lower frequencies. When you have cavity resonators, they are difficult to scale to low frequencies because they get very big. And when you use the electrics in the resonators, then you can actually, because of the higher permittivity, we can do this kind of filters even at 70 gigahertz, because there's a lot of interest, like at 60 gigahertz or 94 or 70 gigahertz. People would like to use our filter technology, but it's getting very big. So all these silicon micro machines means that you cannot do devices which are like 10 centimeter large or something like that. It's impossible to use this at much low frequencies. But dielectric resonators actually can give you the possibility to downscale to lower frequencies and still having a very compact device. Of course, the electric resonators also have the potential advantage of higher Q factor because you don't have the metal losses. But and actually the electric losses are reasonably good in many materials, like even silicon. We are using high resistivity silicon for the electric resonators.
You can use resonators with Wishpring gallery modes.
Yes, that you can also, that people have done that. People have used these whispering gallery modes for bulk acoustic wave resonators at lower frequencies. That's typically done below 5, well, it's in the order of 10 gigahertz. But these filters that I'm showing you here, they're not acoustic filters. They are electromagnetic filters.
Thank you very much.
Thank you for your questions.
Any questions, colleagues?
Yes, of course. Dear professor, could we come back to the antenna array system slides?
Yes.
Okay. Could you explain how it possible to provide antenna beam steering in here in the base of this technology?
Yes. So in this antenna array, we have no beam steering. This antenna array is a so-called corporate FET antenna array. So we have one single waveguide port. Then we have a power distribution network inside this chip. I actually can show you that also. If you want to see some details, I can show you the different presentation. It's a very, very complex device, actually. See if I find this quickly. Should be around here. No, let's see. Yeah, it's around here. We see that. So this antenna, this single chip is a very compact chip, like 20 or 30 times 30 millimeters, 1 millimeter thick, but it contains a power combining network here. It's a very complex network structure in here that you can feed from a single port, like from a single port. You distribute the power to all the antennas. And then you, of course, want to have the same phase front on all the antennas. So this array has very, very low losses, but it cannot do any beam steering. So here we don't have beam steering. But what I showed you in the very end of this presentation is this European project here at the bottom. And this is a new project which we're working on. And here we have integrated phase shifters. In every antenna element has an integrated phase shifter. And this is based on electro-optical modulation. With this, we can do beam steering also. The beam steering of this other antenna array, this one here, the beam steering here happens by having a leaky wave antenna. There's a leaky wave antenna array, actually, because it's a parallel plate waveguide structure. So we have a leaky wave antenna structure integrated here. And here we do the beam steering by frequency sweeping, which is, of course, a very bad way. I call it the poor man's way of beam steering. So this is, of course, not what you prefer to do, but it's a very simple system because you don't need any reconfigurable elements. You don't need any phase shifters. But in this project here, I don't have any results to show yet on this. We will have active phase shifter elements in every antenna array, and this is a complete reconfigurable phased array for beam steering.
Okay, thank you very much.
So, dear colleagues, does any one of you have any questions to Professor Abrahame? No questions. So thank you, Professor, for your very interesting presentation about terahertz devices and micromation technologies. We sure that such devices as filters, diplexers, and antenna arrays for beam forming and beam steering will find its application in 5 and 6G communication technologies. We are moving forward, and our next speaker is Associate Professor Irina Kononova from Igor Sikorsky Kyiv Polytechnic Institute. So, Irina, please start your speech.
Шановні колеги, доброго дня. Шановні студенти, сьогодні вітаю вас на відкритті конференції. Сьогодні я представлю вам наш проект, який називається 500 новин інфотелекому. Сподіваюсь, ви бачите мій екран.
Так, видно.
Дякую. Ну і проект 500 плюс новин інфотелекому. Можу сказати, що оскільки навчально-науковий інститут готує фахівців для сфери телекомунікації, ми систематично подаємо в нашому телеграм-каналі та на нашому сайті інформацію про новини в сфері телекомунікації. Сама ідея створення дайджесту виникла у Михайла Єфімовича ще в січні 2020 року. І вже в лютому 2020 року ця ідея була реалізована. За весь період створення дайджесту було опубліковано всього 920 новин. У 2020 році 333 новини, у 2021 році 486 новин і вже на початку 2022 року на даний час опублікована 101 новина. Однак ми на цьому не зупиняємось, і новою реалізацією, реалізованою ідеєю став збірник найцікавіших дайджест новин, який ми назвали 500 плюс новини інфотелекому. Саме цей дайджест він розділений на 6 розділів. Перше – це стан інфокомунікації України та її межами. Друге – технології інтернету речей та LoRaWAN. Третє – фіксований та мобільний інтернет. Четверте – сучасний супутниковий зв'язок. П'яте – це наступне покоління мереж 5 та 6G. І шостий розділ, який висвітлює новини Міністерства цифрової трансформації України. Якщо починаючи з першого розділу, то можна сказати, що перший розділ висвітлює розвиток телекомунікацій в Україні. Саме зв'язок є одним з найбільш стійких секторів економіки, а розширення Європейського Союзу створює поліпшену ситуацію на шляху подальшого як технічного, так і економічного, так і соціального розвитку. З впровадженням новітніх інфокомунікаційних технологій зв'язок постійно розвивається дуже швидкими темпами, створюючи умови для прискореного економічного та соціального розвитку країни і саме нашої України. Україна брала участь і у будівництві міжнародних волоконно-оптичних ліній зв'язку як для забезпечення власних потреб, так і з метою забезпечення транзитів через її територію. І за останні роки в Україні вже побудовано близько 40 тисяч кілометрів волоконно-оптичних ліній зв'язку. І щорічне будівництво волоконно-оптичних ліній зв'язку в нас вже доведено до межі як 4 тисячі кілометрів на рік. Тобто можна сказати, що потужним зовнішнім фактором впливу на розвиток телекомунікацій України є використання зарубіжного досвіду і впровадження новітніх засобів телекомунікації. Другий розділ розглядає технології інтернет-речей та LoRaWAN, бо однією з основних тенденцій розвитку сучасних інформаційних систем та технологій це є розширення доступності інформаційно-обчислювальних ресурсів в мережі. І сьогодні пристрої інтернету речей не лише масово використовуються у щоденному вжитку, а взагалі використовуються в сучасному бізнес-середовищі. І підкреслюючи, що, зокрема, інтернет речей, він впроваджується в різноманітних галузях, починаючи від промислової сфери до сільського господарства, рітейлу та будівництва. І розвиток технічних засобів і підвищення активності доступу до інформаційно-обчислювальних ресурсів, саме підвищують процес і підвищують інтерес до проблеми ефективності використання мережевих ресурсів інтернету речей, а також забезпечення оперативного доступу до них. Саме цей розділ буде більш цікавий для викладачів, інженерно-технічних працівників, які саме займаються розробкою технічних засобів і проєктуванням в області інтернету речей. Також для наших студентів, для наших аспірантів і всіх, хто займається телекомом. До того можна додати, що у нас розвивається і буде впроваджена в цьому році нова освітня програма, і студенти почнуть навчання в цьому році саме за цією спеціальністю. Наступний розділ – це фіксований та мобільний інтернет. В цьому розділі розкриваються основні тенденції розвитку України. За останній рік Україна дуже піднялась в глобальному рейтингу швидкості інтернету. Було проведено багато досліджень, і за результатами цих досліджень можна сказати, що середня швидкість завантаження в мобільній мережі в нашій країні вже досягла 10 мегабіт за секунду і досягає зараз до 29 мегабіт за секунду. Тобто ми постійно ростемо і розвиваємось. Також Україна отримала декілька відзнак протягом 4 років, відтримувала відзнаку за найкращу швидкість інтернету. І в минулому році також отримали відзнаку за найліпше покриття. Бо на даний час 90% населення вже має доступ до інтернету, до мережі 4G. І тисячі невеликих сіл отримали за цей рік сучасний мобільний та проводовий інтернет. Четвертий розділ присвячений сучасному супутниковому зв'язку. Завдяки сучасним технологіям користуватися інтернетом в Україні не тільки можна, і дуже легко. І навіть в самих важкодоступних місцях, як можна привести приклад, це в Карпатських горах. Основними компаніями декілька років були, які пропонували послуги супутникового зв'язку інтернету в Україні, це Data Group та KSTAT+. Однак зовсім нещодавно одним з досягненням для нашої країни стало це підключення супутникового інтернету Starlink. Великою перевагою саме Starlink в Україні є те, що зараз є можливість постійно підтримувати зв'язок в нашій найважливішій інфраструктурі. І перевагою ще Starlink є його стійкість до кібератак, до помилок, А середня швидкість інтернету становить приблизно 150-200 Мбіт в секунду, що дуже-дуже для нас приємно. Насамперед можна додати, що наші студенти, як тільки появився Starlink в Україні, зразу почали активно дуже займатися науковою роботою і розвитком цієї ніші. Наступний розділ присвячений наступному поколінню мобільних мереж 5G та 6G. Як і кожне покоління до цього, технології 5G прагнули зробити мобільний зв'язок. Я вибачаю, зараз тривога. Зараз, вибачте. Як і кожне покоління до цього, 5G прагне зробити мобільний зв'язок швидким та надійним. Оскільки все більше пристроїв ми намагаємось підключати до інтернету. Зараз ми маємо всі багато пристроїв, і вони вимагають великої пропускної здатності. Ну, як приклад, наші смартфони вже працюють з потоковою передачею HD, ми користуємось розумними годинниками, в нас постійно ввімкнені камери відеоспостереження. Ми використовуємо, наприклад, датчики для здоров'я. І все це для того, щоб воно безперервно працювало, необхідна велика швидкість, не тільки для того, щоб ми могли підтримувати швидкі з'єднання, а й краще обробляли одночасні запити. Дуже стрімко розвивається мережа 5G, однак багато розвинених країн не зупиняються на цьому і починають вже проводити тестування мереж 6G. Наприклад, як великі корпорації, там Apple, Samsung, вони вже роблять і тестують новинку. Зараз 6G обладнання здатне передавати дані на відстані до 15 метрів зі швидкістю приблизно 6 Гбіт за секунду. Але перспективи, що швидкість буде досягати до 1 терабіта за секунду. Інколи виникає питання, навіщо нам 6G, якщо 5G нам дає достатню швидкість? І відповіддю на це питання можна сказати, що збільшення швидкості передачі даних в мережі 6G не є головною метою. Головною метою є для розробки мереж 6G, тому що в цьому поколінні є нові можливості для мобільного зв'язку. Технологія 6G зараз розглядають саме як засіб, який дозволить об'єднати цифровий та фізичний світ. І це дозволить керувати фізичними об'єктами через їх цифрових двійників. Заключним розділом 6 це є новини Міністерства цифрової трансформації України. Ми постійно слідкуємо за цими новинами, світ розвивається, наші спеціалісти показують неймовірні свої можливості. І всього за 2 роки, як почала працювати активно Мінцифра, вона створила портал «Дія цифрова освіта». І майже 4 мільйони наших українців вже завітали на цей портал, і вони можуть безоплатно повністю отримувати цифрові навички. І на даний час найпопулярнішими стали освітні курси – це цифрові держслужбовці, програмування для новачків, штучний інтелект, основи кібергігієни та обережна кібершахраїв. Мінцифру підтримує компанія Окла, яка надала доступ до спідтестів, і зараз можливо через ресурс speedtest.net отримувати і відстежувати швидкість інтернету в Україні. Ця інформація допомагає дізнатися, в яких регіонах треба оперативно реагувати на проблеми зі зв'язком, і також можна отримувати вже зараз дані по показникам якості інтернету, який надає нам Ілон Маск. Також Мінцифра співпрацює з університетом Швейцарії і почала досліджувати фактори розвитку Smart City в Україні. Вже визначено 12 головних умов розвитку для українських розумних міст. Виділяється основне – це доступність необхідних людських ресурсів, належна IT-інфраструктура, яка є, стабільне фінансування та координація дій між представниками держави і місцевого рівня управління. Все це об'єднується, ділиться успішним досвідом, і головну роль виконує спільнота – це Smart City Club, а також платформа «Дія цифрова». Вже більше 2 років наші студенти знайомляться з новинами, вони читають наші новини, вони нам дякують за те, що вони дуже в зручному способі для себе можуть отримувати найцікавішу інформацію. І навіть декілька місяців назад наші студенти прийняли таку нашу ініціативу і в себе теж почали створювати на своїх сторінках дайджест новини. Вони діляться з нами своїми новинами, ми ділимося з ними своїми. Вони нам постійно дякують, і ми їм за це теж дякуємо. Слідкуйте за нашими новинами, будьте в курсі головних подій та трендів IT-ринку. Дякую за увагу.
Дякую, пані Ірина. Колеги, якщо у вас є запитання до Ірини Віталіївни, будь ласка, задавайте. Запитань немає. Ще раз вам дякую, Ірина Віталіївна.
Дякую вам.
Що інформуєте нас про новини в галузі телекомунікації. So, dear colleagues, we are moving forward, and our third plenary speaker is Sergey Osipchuk, Associate Professor from Igor Sikorsky Kyiv Polytechnic Institute. Sergey, please begin your presentation.
Hi, colleagues. Nice to see everyone. Let me share the screen, please. 1 second. Hopefully you can see my screen, colleagues.
Yes, we see.
Okay. Yeah, thank you. So nice to see everybody. It's a pleasure for me and honor to present this today. And yeah, my name is Sergey. I'm working in Institute of Telecommunication Systems, and we will be talking today about some modern trends of Internet of Things technologies development that are very actual and emerging last year, let's say. So moving on. So this will be our agenda about digitalization, IoT applications, 5G, 6G, other applications of Internet of Things, less may be discovered and presented in Ukraine, but still like emerging. And yeah, a bit about what we are doing in Institute of Telecommunication Systems as well. So moving on. So global digitalization. So why we're talking at all about Internet of Things? So I believe that everybody is less or more is familiar with these technologies and maybe even using some of those on the practice in life on daily basis even. And it's not a secret, and even looking at this picture, we can see that, yes, we have everybody like smartphone, we have a lot of things around us. We use some of those and gather data, and that's everything. By following this small example is following the digitalization idea to have everything in digital form, to gather data, to analyze it with some purpose, and usually for the purpose is to make some decisions about the next steps or maybe how to handle the data and what to do with that. So Internet of Things finally is one of technological trends and tool, as we can see, and as it mentioned in the whole digitalization world process. So that's why we are considering it here. So what is Internet of Things? Maybe everybody hears that everywhere, but overall, it's an info communication network of interconnected physical devices, in other words, things, equipped with respective and right electronics, software, sensors, communication technologies, right, that allow people and Internet of Things platform connect to data network, collect data, share, analyze, and basically what is increasing efficiency from some extent, economical benefits, and reduction of human workload. How do we use it? Again, having all that information in hand, we can see what to do next if it's worth to do. So that's the Internet of Things definition, and that's important to keep in mind and remember, understanding if we are talking about any technologies or whatever is related to Internet of Things. Moving on. Threefold concept for Internet of Things. So when we talk about Internet of Things, it's important to remember three different layers. In this case, it's mentioned as and named as applications layer. It could be what we are familiar pretty with: smart home, smart city, digital health, mobility, and others. Communication infrastructure, what is delivering data from the sensors to decision points or applications. And the third layer is information processing and decision-making layer. That's about threefold concept in general, but if we talk about telecommunication component of this story, it's just being split to three different layers, again for 3 layers, but not related to previous, related only to second point of communication infrastructure. And that's about information pulling from infrastructure and sensors from Internet of Things objects, then transmission of those responses to decision points, and what is the most important in this story, so what do we do with that information then? Information transmission to maybe some third parties or recipients after making respective decisions. So why it's important? It's important to remember that concept when we think about some solutions, applications, and everything around that when talking about Internet of Things. Architecture. Architecture is pretty connected about threefold concept, but just maybe in some different representation. So we see 3 layers here. Again, perception layer, what is basically presented by some physical systems, sensors, and responses from those are important for us. Networking layer is just gathering information and transmitting that to the right application layers and databases or whatever platforms it works for further analysis. And the top layer, application layer, it's the platforms and systems that basically processing those responses and providing those maybe responses to decision makers and third parties. Next one, stakeholders of Internet of Things solutions. Why it's important? When we think about Internet of Things direction overall, it's important to understand the parties and stakeholders, and basically what we have here, and these stakeholders can be connected to different layers that we have just seen. It's telecom operators who are taking care of transmission part, Internet of Things platform that provide capabilities for serving the data gathered from sensors and then maybe processing the data, and as well as some application development services for processing the data. Third one is service developers who basically design and create Internet of Things services. And the third stakeholder or party here is service providers, those who like launch, run, and manage, maybe enhance or whatever. But at the same time, all these parts are important. It does not mean that for every single stakeholder, it's different company or stakeholder. There could be like joint solutions. However, yeah, such split, it's important also to keep in mind. And fifth, expectedly, so IoT service consumers, whoever it would be, just some physical like personalities, let's say, or people or organizations. It's about consumers. Moving on. Applications. So applications, there are a lot of different applications. And on this slide, we can see just the directions and fields. So from top to right, agriculture, mobile and embedded, energy consumption, security, telemedicine, smart homes and cities, building management, everyday things, a lot of those. And all those basically growing because there is some need. And that's what we have. And that's what is having a place today and what is growing on daily basis, again, based on the humans' need. From this point of view, just to provide some maybe real examples about what those Internet of Things examples could be and how those examples and cases impact the business. So in this list, we see a couple examples, 8 examples mentioned. That's about, let's name it business transformation. So that's how Internet of Things influenced business. For example, just let's discover 1 or 2. So coffee machines. So there is one, and not one, but just in this case, particular one, who was a provider of coffee for consumers. And there was a question about the most efficient proposal to consumers of coffee. And the question was, how many coffee and what type of coffee are in the need of customers? What coffee is more popular? What is less popular? And there was a very simple decision and solution made, like gathering information from coffee machines equipped by specific sensors and equipped by networking elements to see the statistics about what coffee is used, in what amount, what is more popular, what is less popular, what finally and obviously was positively impacting the business overall. In the same way, we can see other examples like utility meters from the perspective of comparison, manual and automated resources, not resources, but amount of used water or resources gathered. So minimizing human resources for that activity, minimizing human error, automation, making those activities performing on time and so on. Another one is about carriers movement, about shifting different like goods, where those are located and so on. Fourth one, taxi services, so very popular now, but previously, as we know, it was heavily used by phone number, and others. Garbage cans monitoring, patient health, and we will discover later about healthcare, stations of electric vehicles, vending machines, and many others. By this link, we can see a lot of other examples. So to summarize, so IoT is really transforming the business, our life, and that's why it's popular, and that's overall why we are talking about that. Moreover, it's a connection of different components, telecom, information components, and many others. IoT in Ukraine. So just 2 words about whether it's actual or not in Ukraine. So this slide just very briefly shows whether there is a demand for IoT technologies in Ukraine. Short answer is yes. Obviously, as for many other countries in the world, it's needed for personal use and for companies use. And as we can see, there are clients. There are also some concept and applications, things and sensors, providers that are also growing, coming to the market and serving for those clients that I mentioned, and respectively third parties also that are involved based on the decisions made on the gathered data. So it's actual, it's emerging. On this slide, we can see example of services that have been provided. One of Ukrainian providers, it's IoTJI, the link number 4 in this list. And as we can see, there are different services like street lighting, industry, smart parking, and many others.
Сейчас я раз и вышла с конференции, все. Так а чего выйти с...
Larissa Sergeyevna, yeah, thank you. Okay, so overall, what we can see is that, yes, that's one example of companies that is providing IoT services, and together with that, we have other companies, and following that example and split of stakeholders, we can see that cell operators are presented in Ukraine that are serving as cellular network operators, as well as IoT Ukraine, that is basically providing services based on LoRaWAN technology that we heard on previous report. Yeah, Kyiv smart city and digital applications. So smart city example of application and services, and many others. So in summary, it's actual in Ukraine. It's emerging. We have also many examples already working, not just like in theory, but in practice, and that's where we are. So moving on, we are moving towards 5G and 6G. Yes, 5G is well known, implemented in many places, not in Ukraine yet, however, but at the same time, what we have seen in 5G is just a kind of sensors, gateways, 5G links, if those are presented based on some networking operators, and pulling that information, gathering on some application layer, whatever platform it would be, some maybe clouds. And on this table, we can see a list of services like different and differentiated services, smart homes, transportation, e-health. And if we look at this on high level, it's shown like not connected things. So just different, let's say, Internet of Things services that are using 5G infrastructure for gathering and delivering data. But 6G is coming, and what does it mean for us? It's about other technologies, better percents. It's about set of new technologies. Some of those are listed, here, EMMB and others. It's about using other data rates, other and enhanced security, frequencies. We're going to terahertz band, right? And other parameters here. So looking at this, yeah, it's a time for moment from 5G to 6G. And what is the most important we can see on this slide. So 5G, as we have seen, it's about different IoT applications not connected, but when we talk about 6G, it's coming as another layers of telecommunication. What is about space devices and as well as drone devices, drones layer, and as well as sea communications, and all that is working together, like pulling the data using different technologies, and that's about all about 6G. There are some applications of 6G IoT we can see. So as well as in 5G, it's healthcare, but again, following new approaches and technologies. Vehicular Internet of Things, and we will see on the next slides one of great examples what shows difference between 5G and 6G, and how it's aligned with using IoT. Unmanned aerial vehicles, satellite Internet of Things, and industrial Internet of Things, at least 4.0 and plus. So on this slide, we can see it's a kind of a bit overloaded, but it shows the general idea that everything connected with everything, what was not pretty the case of 5G. And on this green square, we can see example of vehicular Internet of Things, what will be expanded in details on next slide. And as we can see, healthcare, one area, vehicle, another area, industrial, third area, everything is connected to maybe cellular, as on this example connection, while there are ships that are connected also via drones or satellite communication, and all that is working together for some purpose. If we move to this example of vehicle autonomous driving in 6G, this example shows really good idea about what is 6G, and let's follow from the bottom to top. So we have connected vehicles to the network. Those are unmanned, yeah, so there is no driver. So data is being gathered. So data is being handed over using network layer capabilities to some application layer, to cloud or whatever. And on application layer, there are different machine learning models and algorithms, strategy, etc. What is finally helping to these vehicles to make a decisions how to move further? What will be not possible in case like every single car in this story would be deciding what to do next, where to turn or where to change the line on the street, right? And having all that, it's just the simple answer. What is the difference between 5G, 6G, and IoT role in this story? As we can see, just in short, 6G, IoT, terahertz band, blockchain as well, from some extent, and machine learning are presented on this slide. Moving on. IoT enabled healthcare. So the same another good example where we see cars, people who are in hospitals or at home, and information gathering about how they are doing, what's going on, some parameters of health. So gathering all the data allows you to make some decisions about what is worth to do next, whether it's worth to action or not. Another one is blockchain. It's really coming as a trend also in maybe last year or two in IoT direction. And just in short, what is blockchain? Distributed database, database in the network, and why it's worth to consider it, and in what cases. IoT enables devices across internet to send data in the manner that the data will be tamper resistant, yeah, of shared transactions. For example, what could it be? There are many applications, especially after COVID-19, that it would be good to know who has maybe got COVID and how people around impacted other people around those people. And there are some solutions based on mobile phones that and applications respective that allow using like Bluetooth technologies or other technologies for short range communication to detect and predict who is impacted or not by COVID, or maybe potentially could be impacted. And blockchain is a good example that allows to record the gathered data across different devices, and it's not possible like to change the data easily. And what shows again tamper-resistant records, right? What is important here for what are the benefits of using blockchain? It's immutability. What about not changing information? Not easy change. Publicity, decentralization, so it's spread across devices. Resiliency, security, also as a result of all these actions, and speed. So here is just short architecture, and what we can see on this architecture is that here is the blockchain layer. What is not like layer that we can touch, but the layer that is delivered based on the devices and the logic implemented around this. Okay, so that's about blockchain. It's also emerging, important. And yeah, moving on. Another one, Internet of Drones. So drones is another layer that is pretty famous and popular, and it's a part of 6G, as we have seen. Overall, it allows, using drones allows achieving different goals and executing different tasks, like some of those I mentioned here. Drone swarms to solve specific questions, both in life and maybe in some military applications. Logistics, also just from the delivery perspective, and one of those was example during COVID to deliver some goods from medical perspective. And yeah, service relaying, it's about transmitting and providing capability to for internet access. So here is on the screen, we can see just a kind of architecture and main connections. On the example on the left bottom side, we can see example of delivering some medical things during COVID time to avoid humanity like touch and connection. So Internet of Drones is very also popular and emerging today. So short one, but important one, security. From some point of view and some sources, some researchers name and ask a simple question: is IoT not Internet of Things, but Internet of Threats? Yes, there are a number of technologies, ZigBee, BLE, LoRaWAN, and others. There are different layers, information, access, functionalities, and there are known vulnerabilities for all those technologies. So we always need to keep in mind that security is an important question. Not everything is super secure, and based on the applications, it's worth to select right technologies to secure the solution. And the last one, IoT in Institute of Telecommunication Systems, just a bit what we are doing with our students, what we are learning, and as was mentioned today, there is the program is coming for the next year. So some solutions in green selection, that's what we were able to deliver and create a solution for temperature metering solution for not for, but based on ESP technologies on Belink platform, open source, IEEE 802.11 technologies. And yeah, that's how the production process was going. Our students and result in form of graph of gathered like data, and the developed device that was working, connecting to the network infrastructure and sending data. Another solution is about water and energy metering control based on Raspberry Pi, OCR recognition technologies for pictures and text. And finally, yeah, it's about also automation and simplifying human resources and life. So that's just was a small word about what we are working from IoT perspective in our institute with students. And thank you, colleagues, for your attention. Welcoming questions, please, if any.
Dear colleagues, if you have,
I have some question.
please.
What distances will be typical between base station and customers in 6G technologies for different types of base station? For example, Earth station, flight, base station, and so on.
Yeah, thank you. Thank you for the question. So basically, I have maybe just very high level and short answer. It's about, if we talk about end device connection, and as we have seen, there are terahertz, so it's coming to shorter distances, right? Than in 5G, let's say. And for all others about drones and satellite, so different like satellite levels. So all this should be discovered, so I can't provide the exact, but yeah, I think that if about drones, then it's some maybe hundreds of meters or maybe maximum kilometers and so on. So in all those architecture, we have different components on different like distances, height, and such physical parameters, and respectively technologies should be used and adopted respectively.
Thank you.
Thank you.
Any questions, colleague? No questions. So thank you, Sergey, for your interesting presentation about Internet of Things and its implementation in our life.
Yep, thank you very much.
So, dear colleagues, our fourth speaker is Alexander Kogat and Igor Kuzmichov from Institute of Radiophysics and Electronics, Kharkiv. The report is titled as Application of Open Resonators to Research the Metamaterials Properties in the Extremely High Frequency Range. Unfortunately, due to hostilities in the Kharkiv region, and as a result, there is no possibility to ensure safety of speakers and no reliable communication between Kyiv and Kharkiv. The speakers cannot now present us his reports online at plenary session. So you will find its report more detailed in the proceedings of our conference. Our fifth speaker is Sergey Kapshtyk, Associate Professor from Igor Sikorsky Kyiv Polytechnic Institute. Sergey Volodymyrovich, please begin your presentation.
Thank you very much. Just a moment, I will start the presentation. Okay, is it okay?
Yes, we see your presentation.
Dear Chairman, dear guests, in behalf of a group of authors, let me to present to your attention the report High-Speed Earth-Moon Information Transmission System for information support of the missions for studying and colonization of the moon. This report was prepared by a group of the lecturers and students of Institute of Telecommunication under supervision of Dr. and academic Mikhail Ichenko. Today, the attention of scientists and researchers from different countries is increasingly focused on the moon. Many lunar missions are developed. These missions predict research on the moon, mining, and colonization. Scientists and engineers are developing and designing a lot of technical equipment. There are automatic landers and rovers for lunar surface. Sorry. Lunar surface. There are automatic landers and rovers for lunar surface studying and research, and automatic small satellites for to provide research from lunar orbit. A separate field is the development of technology and technical mining facilities. This technology and equipment could be used in automatic and distance control modes. The main goal stays the colonization of Moon. For this matter, the technology of long-time habitation is developed. The space agency of different countries are looking at the Moon as a lunar pole and a launch point for the future space exploration mission. All these programs are needed for information support. So the development of the technologies and system for information support human activities on the Moon is actually Project LunaNet. This project is developed by NASA, USA.
Excuse me,
LunaNet says,
Sergey Vladimir,
Yeah.
we see only first slide. Your slide
Sorry.
is not moving.
is it Lucien?
No, only first slide.
Okay, I'll walk in this mode,
Oh.
okay?
Now it's all right.
Lunar project LunaNet. This project is developed by NASA. LunaNet system will help establish a constant and long-time presence on the Moon. LunaNet will provide communication and navigation service that will make it easy for devices to communicate with each other and with Earth. LunaNet is expected to include 3 categories of services. First, networking services. Networking services capable for moving data between nodes and meet confidentiality, integrity, and availability requirements. Next service, position, navigation, and timing service for orientation and velocity determination, as well as time synchronization and discrimination. The service could be used for search and research, surface navigation, and location tracking. Next, science service. Science service providing situational alert and scientific measurement that could not only future research, but also support predictions of major solar and affect space weather and provide information about space radiation. The core of telecommunication subsystem or LunaNet is daily distribution tolerant networking, DTN. This ensures that data flow seamlessly through the network and reach its final destination despite potential signal dispurities. In the event of dispurities between the 2 LunaNet nodes, DTH enables 2 nodes to store data until the path becomes clear. For lunar navigation, the LunaNet approach offers operational independent form data processing on Earth while maintaining high precision. The architecture will provide mission with access to key measurements necessary for onboard orbit determination and guidance system operations for surface position. LunaNet service, LunaNet science service will provide nodes with for the benefit of research on Earth using the radio and infrared optical communication link. The network of nodes could provide operational for baseline observes of the Moon and frequent measurement to provide comprehensive study of the lunar environment in the time. Additionally, the placement of nodes will allow for regional or global observation of the Moon, offering scientists access to lunar data over the large access. Next project, Moonlight. This project is developed by ESA. Having one system dedicated to lunar telecommunication and navigation could reduce the design complexity flexibility, liberation, mission, and competence of the core activity. If this work be outside to consumer of space companies, if this work were outsourced to the consumer of space companies that could put a constellation of satellite around moon, each mission would become more cost-effective. This project predicts the development and put into the lunar orbit of the constellation of communication and navigation satellite. Each satellite will provide direct communication service between customers on the moon surface and Earth. Quadra project, China. Quadra relay satellite, also known as China 4 relay, is a communications, relay, and radio astronomy satellite for Change 4 lunar far-side mission. As part of the China Lunar Exploration Program, the China National Space Administration launched this satellite in May 2018 to a halo orbit around the Earth Moon L2 Lagrange point. This satellite is aiming to support the utilization of lander and rover, which were launched in the framework of China Moon Far-Side Research Program. The satellite is equipped with two different kinds of antenna, a parabolic antenna and several spiral antenna. The former, which has large the antenna, which has large diameter 4.2 meters, was designed to send and receive signal in the X band. It means 7-8 gigahertz to and from the rover and lander of the surface of the moon. Its large size is related to the expected noise level at the low intensity of transmissions that are sent by surface equipment. In addition, the satellite provides connection with small scientist satellite in lunar orbit. The above information shows that the task of development communication and information Earth-Moon system is actually. In the next part of my report, I'll present the concept of the high-speed Earth-Moon information transmission system for information support of mission for studying and colonization of the moon. The main goal of the system is to provide high-speed connection between the Earth Internet segment and moon missions for international and national moon missions of the different countries. The system combines two main parts, Earth segment and lunar segment. Earth segment consists of the Earth receiving transmission stations with a big antenna. Taking into account the rotation of Earth, to provide the constant 24/7 service, it will be necessary to use several antennas, which a relative longitude is around 16 up to 120 20 degrees. This antenna should be located over the world. Earth station will connect with the internet backbone. Consumer of the system will get access to the capacity of the system through the internet. The system will provide service for next group of consumers. First, Moon Mission Control Centers and Moon Mission Data Control Collection and Processing Center. Next, Scientist Research Center, universities and academic institutes. And next, Industry Information Center of company, which will provide mining of the moon. For this matter, the Earth segment will be connected with big data centers to support the activity of consumers. The creation of data center near Earth station would include the information would increase the information productivity of the system. The capacity of this data center will be used to support lunar activity through cloud calculation, data collection, and fast information exchange. Moon segment. Moon segment is established by the Moon Autonomous Land Module. This module provides the connection with the Earth segment and access to the system capacity for the customer's lunar facility, including satellite communication system in the lunar orbit. The module will be located on the polar area and to provide constant power support for onboard equipment for Sun. For the design interplanetary communication and information system, it is necessary to take into account the features of the Moon movement around Earth. The Moon moves on the elliptical orbit with a small eccentricity. The average radius of the Moon's orbit, 384,404 kilometers, and changes from 356,000 up to 406,000 kilometers. The Moon's orbit plane is inclined to the ecliptical plane at degree 5.15. The Moon's equator plane is inclined to the Moon's orbit plane at degree 6.7. Due to this feature, a pair Moon's libration in the meridian directions plus minus up to 7 degrees and in the parallel direction up to 7.5 degrees. As a result, the polar area of Moon is temporarily invisible from Earth. To establish constant connection and to provide information service in mode 24/7, it is necessary to install two modules in the polar area. The Earth segment of the info communication system is created with the involvement of big antennas with diameter 25-32 meters. Usually, these antennas are used as a radio telescope. The use of technology inherent in radio telescopes, in particular, the technology of radio interferometry with unlodged base, can significantly improve the receiving of information flow in the direction from Moon to the Earth, and thus improve the reliability of the information rate in this direction. For example, the radio telescope RT-32 of National Space Facility and Control Center, which was made in the base of communication seabed antenna Mark B, could be used in this system as a receiving system. The backup for this antenna could be used antenna the same diameter 32 meters in Latvia radio astronomy center. The general view of landing module is present in this slide. The autonomous module is designed in the base of modern geostationary satellite with modification to provide landing and long-time operation in the Moon's surface. The module is equipped with a propulsion system that has to provide a soft landing on the Moon's surface. The module is equipped with special framework construction for landing and long-time stay. The module is equipped with big offset L and S band antenna with diameter 8 or 16 or 24 meters. The solar array is mounted on a special extended tower. The solar array revolves following the movement of the sun. For this, the drive of the solar array is mounted on the top of tower. The antenna for radio links for connecting customers radio equipment radio equipment are installed on the tower too. The communication and information payload of the module is present in the slide. The payload consists of the three parts: LS band transceiver, which support connections with Earth segment. The transceiver includes RF transmitter, RF receiver, DVB-S2X modem, and antenna steering unit. The subsystem of customer radio access. There are several two-direction radio modems with antennas. The onboard data center. The equipment of this data center includes a lot of application services, servers, processor to establish computer capacity for customer directly on the moon surface, and data storage. The onboard data center will provide the first stage of cloud computing and data processing before it will be transmitted to the Earth segment. The capacity of onboard data center would be used for artificial intelligence technology for Moon's information system. The router provides information flow routing. The feature of the proposed intercommunication system are the utilization of the big antenna in the autonomous modular. The technology of the big onboard deployable antenna for geostationary satellite was developed around 2000 years. This technology was successfully used for the first generation of Inmarsat satellites and for Terahertz satellites. The art picture of Inmarsat 4 with deployable L-band antenna is shown in the slide. ESA provides the same design. The photo of the ESA's deployable antenna is shown too. The big antenna for the autonomous module will be designed in the base of these constructions after modification and adaptation to the Moon's planetary environment. Big diameter antenna establish narrow beams. The table on the slide shows the estimation for antenna wide beam. Sorry, I'm sorry, just a moment. The table on the slide shows the estimation for antenna wide beam. The visible angular diameter of the Earth for observation from the Moon surface is around 1.8 to 0.1 degree. Currently, the antenna of the Moon has been able to track a movement of the Earth. Initial data for the rough estimation margin of radio link Earth Moon is presented on the slide. The LS band are chosen for Earth Moon radio link. The radio regulation allocates several bandwidths for space radio services in LS frequency band. The advantage of these frequency bands is low free space loss in comparison with the other bands which are allocated for the space service. The additional advantage of the utilization of this big is the utilization of big antenna. This antenna establishes a narrow beam and is located in area with low noise level. However, the Earth station antenna will be not affected by terrestrial radio facilities and will not make influence terrestrial system. I believe the allocation for bandwidth in LS frequency band for interplanetary communication would be successfully resolved by ITU as it will be necessary. For our calculation of the Earth-Moon radio line was taken initial data which are presented here in table 2. This makes central frequency, distance, module antenna diameter, it means on the Moon surface, Earth station antenna diameter, radiated power, module noise temperature, and Earth receiving system noise temperature, rate C to N for frequency efficiency 4 or 4.5. The requirement of the C to N rate was taken from DVB-S2X documentation. That depends on the frequency efficiency. That depends of the frequency efficiency of the from the C to N rate is presented in the slide. As it is seen, to provide frequency efficiency 4 up to 4.5 bit per hertz is needed to get a rate C to N around 16 decibel. This slide presents the result of rough estimation of radio link budget margin. As it is seen, the radio link with big antenna has extra margin for the radio link. It makes possible to reduce radiated power of the module or to increase bit rate of the radio link. And conclusion. Lunar exploration mission need information support from the Earth segment and Earth information system. This issue can be solved by creating an info communication system with an autonomous module located on the surface of the moon. To ensure the functions of the Earth-Moon intercommunication system, it is planned to land autonomous module in the surface moon. According to the design solution and the compressions of the main equipment, the autonomous module are close to the geostationary satellite with certain upgrades that takes into account the need to land and provide long time operation of the module on the lunar surface. The use of big antenna in the lunar and Earth segment of the info communication system requires the equipment of the antenna system of the autonomous module, which means of control and orientation of receiving and transmission beam. A rough calculation of the radio link budget show that the use of big antenna on the Moon-Earth info communication system and the length of the module antenna 16-24 meters of Moon surface provide high extra margin for link budget. It allows use modulation with high spectral efficiency. Thus, the proposed achieved for the of the Earth-Moon info communication system has great margin to increase bandwidth and increase the volume of information exchange. Thank you for your attention. If you have some questions, I am ready to answer.
Dear colleagues, please put your question to Sergey Volodymyrovich if you have them. So there is no question. Thank you, Sergey Volodymyrovich, for your interesting presentation about lunar mission and the projects for communication organizing between Moon and the Earth.
Thank you.
So, dear colleagues, our final report is from our postgraduate student, Bogdan Zadoyenko. Bogdan, please begin.
Good afternoon, everybody. I want to open my presentation. I hope you see my screen?
Yes, we see your screen.
Presentation.
Yes, we see presentation.
Okay.
Everything okay.
Okay, thank you. Our subject is ontology-based approach to scientific institution information representation. Our team, Professor Globa, Larissa, and Associate Professor Rina Novogrudska, and also PhD student from China, Eugene Feng. This project, we work for China. Today, there are a large number of public and private institutions providing services in various spheres of social life. The demand for such institutions depends on the efficiency of their functioning. For organizations involved in the fields of science and education, the efficiency of their functioning is particular importance because the quality of the service they provide depends on the future life of the state development and the life of each citizen. Our research work built on government documents. It's like regulation on the state certification of research, scientific and technical institution, methods of optimization of budget research institution, which are fully or partially funded by the state budget, procedure for assessing in the development of the scientific institution approved by the Cabinet of Ministers of Ukraine. In the course of scientific institution functioning, they accumulate a great deal of information that can be used to evaluate them according to the national principles. Problem of the scientific institutions information analyzing and processing arises especially in order to automate the evaluation process of such institutions. The idea to systematize and structure such information using modern means of artificial intelligence can solve such a problem. The usage of ontology as one of the knowledge representation models can implement scientific institutions information organization for its structuring and systematization, its further processing and use. The research proposed the approach to ontological model development for the presentation of information accumulated by various scientific institutions and organizations. It involves the design of the ontological models, structure, the description of ontological model elements, and ontology direct development and filling it with data. Ontologies allows to structure, organize, and classify informations which accumulated in scientific institution. Also, ontological models provides conceptual representation. Its domain concepts and connections facilitate knowledge access, which include information exchange between people and heterogeneous systems. Formal structure, it simplifies computer processing and communicator. It's disciplinary distributed information resource and systems. In our work, we collect the more important indicators of the scientific process. It's the number of publications, the number of citations, it's scientific, technical, and research work, trained specialists of different qualification levels in different specialties and specialization, so on, so on. Process involved in the process of scientific institution activity, organization of institution activity, definition of indicators by which it's possible to identify the level of performance and certain type of activity in an institution. The extent of criteria for evaluating such indicators, which using them it's possible to evaluate the achievements of institution and to determine whether its activity meets the requirements. Organization of the institution's evaluation process itself. On this slide, we can see the schematic model of the layer ontology of what I'm built. We can see what in ontological model use data knowledge and ontology built from different layers, and each layers include some ontology models and information. I can describe this ontology like formula like this, and we can see what this formula includes. Parameters, it's like the set of classes, what's used to describe concepts of subject field, is a set of attributes that are used to describe concepts, characteristics. Also, it's the set of relation specified in classes, the set of attributes, values, standard types, and a set of attributes, value limitations, and set of class data. On this slide, it's a fragment of ontology of institution activities organization. It's a good example for show how it's working. For example, we have class person, and this class have different attributes. For example, person can be a student or some researcher or teaching staff, professor, lecturers, so on. And this person can work in some organization. And where is this organization located? For example, in Kyiv, like KPI. And for example, what event we have? For a good example, we have conference today, and this conference is some event, it's some class of event, and we can describe this event like it's internal conference, scientific, international, and we can see what all classes have interrelations. Also, we subscribe all classes and describe all classes and class attributes, and also give examples for child classes and relations. In my practical work, I'm using transdisciplinary education dialogues of application ontology system. This platform provides the networking with large volumes of unstructured and poorly structured information, semantic content analysis, aggregation and rating of information resources, integration with other network information systems and web-oriented applications, development of ontological interactive documents, also detection of the data in the analysis information resources. On this slide, we can see some examples from information from TEDOS. We can use this platform for different views. We can see a table representation of ontology, and we can see in this table some information. And also, we can see good how layers split in our ontology. And also, we can see graph view. It's an example of the top layer of ontology. We can see it's some rating of institution or university, and this rating built on the rating of lecturer who works in these institutions, and each lectures have own rating from different years. On this slide, we can see I told before what each lecture has different rating, and this rating splits in different ways. For example, research work, different research ways, and also it's split to different type of work. When we open some class, for example, like this in teacher 1, we can see describe of type of work, what to do this teacher in this, for example, the last year, how many points teacher can get for this job, and which part teacher done. And for example, when 100%, teacher done, for example, when we take some research work for some publication, we can get additional points. And this divides when only one authors, we can get 1%. And when two authors, the teacher can get 50% and he get only 25 points. Okay, conclusions. The ontological representation allows to evaluate the quality of scientific institution function on the basis of national principles for such assessment. The information how to organize the evaluation process as well as generally accepted evaluation criteria are also stored in the ontological model. The associative relations between objects that are determined in ontological model allow to link the institution activities indicators with the evaluation criteria for assessment process automation. Future researchers will focus on the future ontology development and its filling with subject domain information, as well as on the novel method implementation for scientific institution functioning assessment based on ontology. Thank you for your attention. If you have some questions, you're welcome.
So, dear colleagues, put your questions for Bogdan. No question. So, thank you, Bogdan, for your interesting report about ontology. So, dear colleagues, in accordance with our program, our plenary session is other, but before we finish, I must admit two notes. The first, in our conference program, there is exhibition of innovative developments in the field of telecommunications. There are 3 posters presented there. The first is the digital system of automation control of sensitive access sensors of targeted action, supervisor Professor Lysenko Alexander. The second is the wireless sensor network of increased functional visibility. Supervisor is Novikov Valery Ivanovich. And the third is development of 2022 to 2020, development of 2021 to 2022 Radio Technical Club Polytechnic UT7UZA KPA Igor Sikorsky, supervisor Sergeyenko Mikola. You can view these poster reports by the permanent link which shown in our conference program. And the second note is at 2 o'clock p.m. Our student 14th International Scientific and Technical Conference of Students and Postgraduate Prospects of Development for Information Telecommunication Technologies and Systems will start. There are 7 reports of our students, so you are welcome to view these reports also. Михайло Єхімович, ваше заключне слово. Михайло Єхімович, мікрофон.
Шановні учасники конференції, ми з вами виконали програму першого пленарного засідання нашої конференції. Я хочу подякувати всім доповідачам, всім учасникам. Дійсно, тільки одна доповідь не вийшла, тому що організація наших співавторів із Харкова не могла під'єднатися через ті дії, які там відбуваються. Зник зв'язок в цій організації внаслідок бойових дій прямо в місті Герої Харкові. От такі реалії нашого життя. Те, що стосується завдань нашої конференції, ми рухаємось далі. Шановні колеги, далі в нас будуть пленарні секційні засідання. Завтра, післязавтра, за програмою, майже всі доповідачі вчора підкреслили свою можливість бути присутніми. І ми з вами зустрічаємось на заключному пленарному засіданні в п'ятницю о 10-й годині. Так, Гліб?
Так.
От п'ятниця, 10-та година. Підведемо підсумки. А так, дякую, шановні колеги, і хай нам щастить разом до перемоги. Дякую. До побачення.
Дякуємо.
Дякуємо. До побачення.
Побачення.
До побачення.
До побачення. Дякуємо.
До побачення.
До побачення.